So last time we looked at the main components of a vapor compression cycle. We're going to get a little more in depth there, but just as a recap, the vapor compression cycle is a refrigeration cycle that accomplishes some cooling in some zone or space, and it uses these pieces of equipment mainly to accomplish that vapor compression. So it's called vapor compression. It uses the compressor and expansion valve and two coils to take vapor at the compressor stage, condense it down to a liquid, start evaporating it at the expansion valve, fully evaporate it at the evaporator when it picks up the heat from the zone, and then starts the cycle back over again. So as we look at the next couple slides, we're going to have this quad chart kind of layout where we're looking at the picture from the field about what this equipment looks like, the different components and where we are in the cycle, the saturation phase and chart and where we sit there, and then just the schematic that shows the basic layout. So we're going to start with the compressor. So in a simple DX type split system, it's going to sit in the condenser, and it's typically going to be a scroll type compressor. And we'll get into the different compressor types and what they look like, the guts of them, in the next couple sections. But for right now, we just acknowledge that it sits in the condensing unit, separate from the condenser coil, and it's responsible for taking in work into the system to pressurize the refrigerant vapor and send it on its way throughout the rest of this loop. And you can see on the saturation chart that we're going to see a little bit of an enthalpy change from the heat that's picked up. And we're going to see the pressure get to the constant pressure line that we see it go at across the condenser process. So the compressor spits out into what's called the hot gas line, and you can see it represented here in both in the schematic and in the condensing unit. So from the hot gas line, it's going to go into the condenser, which is a short trip in this case, and then that condenser coil is going to have that indirect air to vapor heat exchange with ambient conditions with this fan to help get more CFM and get more of a heat exchange. So we can see it on the saturation chart here as a constant pressure process, but we're going across the vapor dome, which means that we're going from a vapor state and we're ending up at a liquid state. So now we're going to have discharge into the hot liquid line. So you can see this coming out of the back of the condensing unit, and that's one of the lines that goes into the space. It's going to be an uninsulated line that's going to go to the expansion valve that's going to be in the evaporator unit. So here we see an example of what that valve looks like. So typically an expansion valve or thermal expansion valve is going to be either electrically controlled, or it could be a pinch in the pipe, or it could be a little valve needle here that's manually set. But its job is to maintain low evaporator pressure. So it's a big pressure drop that, as you see on the chart, at constant enthalpy, because there's no heat exchange here, is going to drop the system pressure down to where it's going to sit at the evaporator. And when you do that, when you drop that pressure down, because of the way that the properties of the refrigerant, that's going to accomplish this temperature cooling, so that the refrigerant in the evaporator is going to be at a much cooler temperature. So now there's a small line where the expansion valve is discharging into the cold liquid line. It's going to go right into the evaporator. So the evaporator is another coil, and in this case it can be considered a liquid to air indirect heat exchanger, and that's what's going to suck up the heat from the zone or from the space, typically with a fan, again to help with the CFM and help the heat exchange. But it's going to capture that zone load, and as it does that, it's going to boil or evaporate. And on the saturation chart here, you can see that it's at a constant pressure. It's leaving the vapor dome, and it's going into that vapor state. And it does that discharging into what's called the suction line, which is this line going into the inlet of the compressor, and you can see that it's insulated, and one reason that that's done is to protect the compressor. The compressor only wants to see vapor. Pumps are for liquids, compressors are for gas. So if there was any type of heat exchange at that suction line, such that there was a little bit of liquid getting into that compressor, it's going to cause damage. So we insulate it to protect the compressor. So this is going to be a cycle that is going to be common to all vapor compression devices and systems. And chillers, as we said, are internally housing this refrigerant loop. So when we look at DX coil, it's a split system. Half the refrigerant loop is inside the space, half of it is outside the space. But in a chiller, that loop and those four main components all sit inside the piece of equipment that we call a chiller. And then it's got these intermediate loops for chilled water that runs out to the space to a coil, and either an ambient air conditioned or condenser water to a cooling tower. But we're talking about the same equipment, but instead of an evaporator coil, we have an evaporator barrel, which is, as we saw in the heat exchanger section, is an indirect liquid-to-liquid heat exchanger device.